To practice with interference, let's consider this problem. We have two speakers. Here's my traditional speaker cone, one, with sound just going everywhere. And below it, we have another speaker cone that is placed 2 meters or 3 meters down. Okay, so we have a distance here. I'm going to give it a variable d. Okay, there's my distance between them. And these speakers are emanating sound in all directions. And my question is, what is happening right here, a distance 4 meters in front of this first speaker? Is it constructive interference, is it destructive, or somewhere in between? Okay, so I'm going to label this one with a variable I'm going to call R1. And in order to figure out if that's constructive, destructive, or somewhere in between, I need to know the path difference. So I'm going to draw another vector, call that R2. And my goal is to find the difference in the path length. Okay, so here's the path, one path length, here's another path length, and I need to find the difference between the two and see how it relates to the wavelength. Okay, some other information I need is these two speakers are driven by the same source. So I have some function generator that gives a single frequency, and so I'm going to say that's some frequency f, and it's driving them together. Okay, so I'm going to ask a little bit later, what does that mean? So my goal is to find, is this point constructive, destructive, or somewhere in between? Let's go and start listing some things we know, and then we're going to have to know a couple constants here. Alright, so what do we know? I know that the speakers are 3 meters apart, so I know D equals 3 meters, and I know it to the 10th place. I know R1 is 4 meters. Okay. I know the frequency is 680 hertz. Remember, hertz is the name for 1 over seconds. So I have 680 hertz signal driving both of them. And another bit of information I need to know is this is sound waves, and we'll assume that the speed of sound in this room that this is happening in is 340 meters per second. So the speed of the sound is 340 meters per second. So that's the information I'm given. I've got some numbers there. What am I trying to find? So I'll put find. Well, generally I like to write a variable here. I could just write out a sentence saying is the position at R1, is that constructive, destructive, or somewhere in between. But I should be able to translate those words into a variable. Like, what variable am I going to look at or look for that will help me know if that condition is met, what condition is happening there? And so what we need to know is that path difference. So I need to find delta R, but not just delta R. I need to find delta R and how it compares to the wavelength. Okay, how it compares to the wavelength. So I need to find these two variables and compare them to be able to answer the question, is that constructive, destructive, or somewhere in between? Okay, with my diagram fully drawn out, with my variables all defined, okay, shown here, and in what numbers I know and then what I'm looking for, I'm now ready to actually do some computations. Okay, so I'm going to draw a line here. Now let's go ahead and consider what we can do with this. Well, it's finding delta R. That is a geometry question, and so I've chosen some nice slick values. D is 3, R1 is 4, R2 is the hypotenuse of this right triangle, and so from that I could just write out 5 meters. We know this is a 3, 4, 5 triangle, but just in case it was something different, and I'd have to be more careful, or I'd have to use some Pythagorean theorem. Let's go and write that out. I'm going to say R2 is the hypotenuse, which should be equal to the square root of the sum of the squares of the two sides. Okay, so it's going to be d squared plus R1 squared. And plugging in 3, squaring it to 9, 4 squaring it to 16, 16 plus 9 is 25, and the square root of 25 is 5. So that's 5 meters. Okay. Alright, so I found delta R. I'm good. Now I need to find the wavelength. Well, where is the wavelength? What evidence do I have to calculate the wavelength? Well, remember that very important relationship for all waves is the relationship between frequency, velocity, and wavelength. You can write that out as the wavelength equals the wave speed divided by the frequency. So with that, I can now plug in my wave speed, 340 meters per second, divided by the frequency of 680 hertz. That's meters per second over 1 over seconds, leaves me with meters. That's good because I should end up with a length here. And I chose those values to be convenient. That is 1/2 of a meter. Okay? Alright, well, I now have lambda. So the question is, what's the condition? Well, let's go back to the main equation that we've used to interpret constructive or destructive. That's the difference in the full phase. So our phase difference between these two waves coming to that point is dependent on the path difference converted to a radian value. So that's what the 2 pi is there. I have delta R, the path difference, over the wavelength, plus any difference in the phase constants, the initial phase coming out of the speakers. Okay. Now I haven't drawn them. I haven't drawn any waves here. But there's something about this that tells me what the value of this is. Okay. The frequency is generated by some box, some device, that's sent simultaneously to both speakers, which means this speaker is receiving the same signal as this one is at the same moment of time. So if that's true, no matter what the phase of this one is, this one has the same phase. So this could be pi, this could be 3 pi, whatever, but this will have the same one. And so since all I care about is the difference, then I can just say that is 0. And so I'm left with, this is equal to 2 pi. My delta R is 5 meters, and my wavelength is 1/2 a meter, which gives me a total radian value of, if I multiply that 2 up, I get 4 times 5 is 20 pi. Okay. And that is an even number of pi, which means that it's a full cycle. So this is a full cycle different, or multiple full cycles, but it's still just a full cycle different, or an even cycle different. So if this one has a crest, then this one has a crest. This one has a valley there, then this one has a valley there. And now there's a little bit slicker way. I could have not even really worried about these numbers directly, and I even encourage you to think about it this way. We could have said that this is 2 pi, and knowing that the wavelength is 1/2 a meter, okay, knowing the wavelength is 1/2 a meter, we could say that the distance that it travels is 10 wavelengths. So that's just 10 lambda, okay, divided by whatever the wavelength was, and we can just cancel out the wavelengths. Okay, get the same answer. It's a little bit, instead of worrying about numbers per se, we're worrying about the ratio of wavelengths it is, and so we can see it there. It's 10 wavelengths different. Okay. Now, so this is our major equation we use for this particular phenomenon. We had to employ this very important, very general wave phenomenon here, and then some geometry. Those were our 3 tools we had to use to be able to solve this. But I want to point out one way of a little bit more efficiently thinking about this. If the initial phase difference, the phase constant difference is 0, so if they're all ever the signals are being generated by the same source, we don't have to really worry about the phase per se, it's all based on the path difference. And so I can change my conditions on constructive or destructive if they have the same initial phase. We can just say that if delta R, the path difference, is equal to 0 or lambda or 2 lambda or 3 lambda dot dot dot, then that will be constructive. That's basically saying it's a full cycle difference. Okay? But if it equals half lambda, 3 halves lambda, 5 halves lambda, and so on, then that is destructive. Okay? So this is really useful to think about conditions where you have the same source, or the sources are generated by the same signal. Because all you care about is the path difference. And again, refocuses, instead of having some generic equation you're trying to just plug into, is what does each piece mean? Okay, and this is really all we care about for a case where the initial signal is this, or from the same source.